Sometimes science sounds like pure fantasy. We talk about black holes, about particles that are in two places at once. We talk about an expanding universe. And then there's the Casimir effect. It sounds like something from a magic show. A force that appears from absolutely nowhere. You take two plain metal plates, you put them really, really close together in a perfect vacuum. And then they feel a push. They are pushed together. A force from nothing, they say. It's a head scratcher. It challenges everything you think you know about empty space. But it's not magic. It's science. And it's one of the deepest, most mind-bending truths about our universe. It tells us that what we call nothing is actually very, very busy. It's a bustling place. And it's full of hidden energy. To understand this force, we first need to rethink what empty space truly means. For most of human history, and even today, when you picture the vast emptiness of outer space, you imagine, well, nothing. Just a void. A blank canvas. A place devoid of matter, light, sound, everything. That's a natural assumption. It makes sense to our everyday experience. If you suck all the air out of a container, it feels empty. Right? But modern physics has completely changed that picture. It's given us a much more exciting and much stranger view of reality. It tells us that even the most perfect vacuum, a place where there's no air, no dust, no atoms, no light photons, nothing that we can usually detect with our senses or even our most sensitive instruments, is not truly empty. Not at all. It's alive. It's seething with activity. It's like a furiously bubbling pot that never stops. Or a wild, frothing ocean. This activity comes from what we call quantum fluctuations. These are tiny, random changes in energy. They happen all the time, everywhere. They're not just happening in some special place. They're happening in every single bit of space, all the time. These fluctuations are incredibly small. They are also incredibly fast. They involve particles popping into existence for a brief moment, and then disappearing again just as quickly. These fleeting particles are known as virtual particles. They're not like the stable particles that make up atoms like electrons or protons. Those particles hang around, they have a measurable mass, they interact in predictable ways. Virtual particles are different. They are more like ghosts. They borrow energy from the universe for an incredibly short time. They exist just long enough to have an effect. Then they vanish. They give the energy back to the vacuum. It's a quick transient loan, and it happens continuously. The rules for this borrowing come from something called the Heisenberg uncertainty principle. This is a core idea in quantum mechanics. It essentially says that you can't know everything with perfect precision. There are limits to what we can measure simultaneously. For example, if you know a particle's exact position, you can't know its exact momentum. There's always some fuzziness. The same applies to energy and time. The uncertainty principle allows for a tiny temporary violation of energy conservation. For a very, very brief moment, energy can appear out of nowhere. It can create a pair of virtual particles and particle and its antimatter twin. They live for that tiny moment. Then they annihilate each other. They return to the vacuum, all within the limits of this principle. So the vacuum isn't just a passive void. It's a dynamic, energetic sea. It's teeming with these virtual particles of every kind. Virtual photons, which are the carriers of light. Virtual electrons and their antimatter partners, positrons. Even virtual quarks and gluons, they're all constantly appearing and disappearing. All everywhere. All the time. It's like an invisible, bustling metropolis of subatomic activity. A constant, unseen dance of creation and annihilation. This constant, frantic activity means that the vacuum itself has energy. Even at the coldest possible temperature, absolute zero, when all ordinary motion stops, this energy is still there. It's called zero-point energy. It's the lowest possible energy state that a quantum field can have. It's an inherent property of space itself. You can't get rid of it. It's woven into the very fabric of reality. Now, imagine those two very smooth, perfectly flat metal plates. Let's say they are uncharged. We place them very, very close together in this quantum vacuum. This vacuum is full of all those virtual particles, all those energy fluctuations. These fluctuations, these virtual particles, they behave like waves, just like light waves or water waves. They have wavelengths, they have peaks and troughs. Outside the plates, there are no restrictions on these waves. The virtual particles can have any wavelength they want. All sizes of waves are allowed to pop into and out of existence. Short wavelengths, long wavelengths, medium wavelengths, they're all equally probable. They all contribute to the overall energy and pressure of the vacuum. It's a full-fledged, energetic party out there. But what happens in the tiny gap between the plates, that's where things get really interesting. The metal plates act like boundaries. They're like walls, or like the ends of a guitar string. When you pluck a guitar string, only certain wavelengths of sound can vibrate on that string. The waves have to fit perfectly between the fixed ends. They have to have specific points where they are still, called nodes, at the ends of the string. It's similar for the virtual particles, or rather for the quantum field fluctuations between the metal plates. Only specific wavelengths are allowed to exist in that tiny gap. The waves of virtual particles must fit cleanly between the plates. This means that very long wavelengths, which would extend beyond the gap, simply cannot form. They are suppressed. Only shorter wavelengths can fit, and even then, only specific shorter ones that conform to the boundary conditions set by the plates. So inside the plates, there are fewer possible modes of vibration, fewer possible wavelengths for the virtual particles. This means that there are effectively fewer virtual particles popping in and out of existence between the plates compared to the space outside. It's like some of the guests at the party have been politely asked to leave, or they simply can't fit through the door. The party inside the gap is quieter. It's less crowded. Outside the plates, the party is still going strong. All wavelengths are allowed. All the virtual particles are coming and going as usual. It's a busy, energetic environment. This difference creates an imbalance. Think of it like a pressure differential. You have a higher density of virtual particles and thus higher energy density outside the plates. And you have a lower density of virtual particles and thus lower energy density between the plates. It's like having more air pressure on one side of a wall than the other, or more water pressure. And what happens when you have more pressure on one side of an object than the other? The object gets pushed. The stronger pressure pushes it towards the weaker pressure. That's exactly what happens to the two metal plates. The pressure from the outside, with its complete spectrum of virtual particles, pushes the plates together. It's not that the plates are actively generating an attractive force themselves. Instead, they are being pushed by the differential pressure of the quantum vacuum surrounding them. It's a push from the outside of the plates, not a pull from between them. This is the very essence of the Casimir effect. It is a subtle but real force, a force that arises directly from the quantum vacuum itself. It's a push from the nothing that we now know is anything but nothing. It's a strange and beautiful confirmation of quantum mechanics. This groundbreaking idea was first put forward by a brilliant Dutch theoretical physicist named Hendrik Casimir. This was back in 1948. He wasn't even setting out to find a new fundamental force. His work was actually much more practical. He was working for Philips Research Laboratories in the Netherlands. His task was to study the properties of colloids. These are mixtures like milk, paint, or fog, where tiny particles are suspended in a fluid. He was looking into the stability of these mixtures. Specifically, he was investigating van der Waals forces. These are weak, attractive forces that exist between neutral atoms and molecules. They are responsible for things like geckos being able to stick to walls. Casimir was working with his colleague Dirk Polder. They were trying to understand how these van der Waals forces behaved over longer distances. And then he had this incredible theoretical insight. He realized that if you place two uncharged, perfectly parallel metal plates very, very close together in a perfect vacuum, the quantum fluctuations of the electromagnetic field between them would be restricted. This restriction would lead to a measurable, attractive force between the plates. A truly radical prediction. Nobody had ever conceived of such a thing. A force generated by empty space itself. It sounded like pure fantasy to many. How could you possibly measure such a tiny, ethereal force? Casimir's mathematical calculations, however, were rigorous. They were solid. He had derived an equation that predicted the exact magnitude of this force based on the distance between the plates and fundamental constants of nature. For a long time, the Casimir effect remained mostly a theoretical curiosity, an elegant piece of quantum mechanics, but seemingly beyond the reach of experimental verification. The predicted force was incredibly small. It was only significant at extremely short distances. And achieving those distances and maintaining them with perfect parallelism and without contamination was a monumental technical challenge. The first attempts to experimentally verify Casimir's prediction were made by M.J. Sparnay in 1958 at Philips, where Casimir himself worked. Sparnay used very sensitive equipment. He managed to get measurements that were consistent with Casimir's prediction. But they weren't extremely precise. The error margins were still quite large. The technology of the time simply wasn't advanced enough to perform a definitive, high-precision measurement. Dust particles, electrostatic charges, vibrations, all these environmental factors could easily overwhelm the tiny Casimir force. It was like trying to weigh a feather in a hurricane. It took several more decades and significant advancements in precision engineering and vacuum technology for truly definitive experimental proof to emerge. A major breakthrough came in 1997. A physicist named Steve Lamoureux published a highly precise measurement of the Casimir force. He used a meticulously designed experiment. Instead of two parallel plates, which are incredibly hard to keep perfectly aligned at nanometer distances, he used one flat plate and one sphere. The sphere plate geometry makes the alignment much easier. The force can still be calculated precisely for this setup. Lamoureux employed a very sensitive device called a torsion balance. This is essentially a very delicate lever suspended by a thin fiber. Even the tiniest force can cause it to twist. He brought a gold-coated sphere very close to a gold-coated plate, keeping them in an ultra-high vacuum chamber to minimize interference. He then carefully measured the tiny twist in the balance. His results were remarkably precise. They matched Casimir's theoretical prediction to within 5%. This was a huge moment for physics. It provided undeniable, high-precision proof that this strange force, predicted almost 50 years earlier, was absolutely real. Since Lamoureux's pioneering work, many other experiments have confirmed the Casimir effect with even greater precision. Researchers have used different experimental setups. They've used microelectromechanical systems or MEMS devices. These are incredibly tiny machines. They are fabricated using techniques similar to those used to make computer chips. Think of microscopic gears, levers, and sensors built directly onto silicon wafers. These devices are ideal for probing forces at the nanometer scale. They've allowed scientists to study the Casimir effect in various configurations and with different materials. The scientific community now considers the Casimir effect a well-established and fundamental aspect of quantum reality. It's not just a theory anymore, it's an observable fact. So, how strong is this force we're talking about? Generally speaking, at everyday distances, it's incredibly weak. You'd never notice it. If you put two ordinary objects, like two dinner plates, a few centimeters apart, the Casimir force between them would be immeasurable. It's dwarfed by gravity. It's easily overwhelmed by the slightest breath of air, or by stray electrostatic charges that build up on surfaces. However, the Casimir force becomes significant and even dominant at incredibly small distances. We're talking about distances measured in nanometers. A nanometer is a billionth of a meter. To give you some perspective, a human hair is roughly 50,000 to 100,000 nanometers thick. So we're talking about distances much, much smaller than that. At these scales, the force grows very rapidly. It follows an inverse fourth power law. This means if you halve the distance between the plates, the force doesn't just double. It becomes 16 times stronger, 2 to the power of 4. If you reduce the distance by a factor of 10, the force becomes 10,000 times stronger. It's a dramatic increase in strength as objects get closer. At distances of a few tens of nanometers, the Casimir force can actually become the strongest force acting between two uncharged objects. It can be more powerful than gravity. It can even be stronger than electrostatic forces that might arise from tiny residual charges. This rapid growth in strength at minuscule distances is why the Casimir effect is so critically important for the design and operation of tiny technologies. And this brings us to one of the most interesting practical implications of the Casimir effect. It creates a problem for nanotechnology. Imagine engineers trying to build extremely small machines. These are called nanodevices. Think about microscopic motors, tiny sensors, or ultra-small switches. These components need to move freely, they need to slide past each other, they need to engage and disengage without issue. But if these tiny parts get too close to each other, the Casimir force, being attractive, can pull them together. It can make them stick. This undesirable sticking is known as stiction. Stiction is a major headache for engineers in the field of micro and nanotechnology. It can cause tiny gears to seize. It can prevent microscopic switches from flipping. It can stop nanobots in their tracks. Engineers have to actively design around this problem. They might shape surfaces to be non-parallel or add special coatings to surfaces. They might introduce rough textures at the nanoscale to reduce the contact area. Sometimes they want to avoid the Casimir force entirely. Other times, they think about how they might actually put it to use. Yes, there's a fascinating area of research focused on harnessing the Casimir effect. Can we use this vacuum force to our advantage? Can we build tiny devices that are powered or manipulated by it? It's a captivating idea. For example, some scientists are exploring the concept of Casimir motors or Casimir actuators. These would be devices that use the vacuum force to generate motion, but here's a crucial point. It's important to remember that the Casimir force, in its usual attractive form, causes things to pull together. If you want continuous motion, like in a motor, you need to be able to reset the system. You need to pull the parts apart again so they can be attracted once more. And that action, pulling them apart, requires an input of energy. So, this is not a magical free energy source. It doesn't violate the laws of thermodynamics. It's not a perpetual motion machine. It's about intelligently manipulating an existing force within the universe. You can use the vacuum's energy to do work, but you can't get more out than you put in to cycle the system. It's like using a spring. A compressed spring can do work when it expands, but you had to put energy into compressing the spring in the first place. The Casimir effect is similar. It shows us that vacuum energy is real and can exert forces. But harnessing it for continuous work still requires external energy input. However, the idea of manipulating this force is still incredibly exciting. What if we could make the Casimir force repulsive instead of attractive? That would be a game changer for nanotechnology. If you could make two objects push each other apart using the vacuum, imagine the possibilities. You could create tiny parts that levitate above each other. They would never touch. They would never experience friction. They would never wear out. That's the dream of frictionless nanodevices. This isn't just science fiction anymore, it's an active area of research in laboratories around the world. And it turns out creating a repulsive Casimir effect is indeed possible. It's not as simple as just using two plain metal plates in a vacuum. You need more complex setups. For instance, researchers have shown that if you use specific materials, especially certain dielectric materials, materials that don't conduct electricity well, or if you introduce a liquid medium between the objects, the force can indeed become repulsive. The key is how the quantum fluctuations interact with the specific optical properties of the materials and the surrounding medium. If the vacuum energy inside the gap can be made higher than outside, then the net force will push the plates apart. This is a much more advanced and nuanced concept than the simple attractive force, but it shows the incredible versatility and depth of this phenomenon. The repulsive Casimir effect, sometimes called anti-Casimir, offers promising avenues for innovation. It could be a way to solve the stiction problem in MEMS and NEMS devices. It could lead to entirely new types of frictionless bearings or ultra-sensitive sensors. The control and manipulation of these vacuum forces are on the cutting edge of physics and engineering. Beyond its practical applications, the Casimir effect tells us something incredibly profound about the nature of reality itself. It stands as compelling evidence that the quantum vacuum is not just empty space. It is a dynamic, energetic medium. It is teeming with potential. It underlies everything we experience. This vacuum energy isn't just an abstract theoretical concept. It has tangible, measurable effects. It exerts forces, it pushes and pulls on objects. For fundamental physics, this is a monumental discovery. It provides strong experimental support for quantum field theory. This theory is our most comprehensive and successful description of how particles and forces interact at the most fundamental level. The Casimir effect is direct, observable proof that quantum fields are continuously fluctuating. It shows that virtual particles are not just mathematical tricks, they are a very real, albeit fleeting, part of the universe. And even if we can't directly see them, their collective presence can be inferred by the forces they create. Some physicists and cosmologists also draw connections between the concept of vacuum energy and the enigmatic phenomenon of dark energy. Dark energy is the mysterious force that is thought to be responsible for the accelerating expansion of our universe. Scientists theorize that dark energy might be related to the energy inherent in empty space itself. The Casimir effect, by demonstrating that empty space does indeed possess energy and can exert forces, offers a concrete, albeit small-scale, example of this idea. However, there's a massive, staggering discrepancy here. The theoretical value for the total energy of the vacuum, based on quantum field theory, is astronomically larger than the amount of dark energy observed in the cosmos. This huge difference, a factor of something like 10 raised to the power of 120, is one of the biggest unsolved puzzles in all of physics. It's sometimes called the vacuum catastrophe, so while the Casimir effect confirms vacuum energy on a small scale, directly linking it to cosmic dark energy remains a profound challenge. But it absolutely hints at the reality of vacuum energy on a much broader scale. It's also important to address common misunderstandings about the Casimir effect. As mentioned earlier, the phrases force from nothing or vacuum energy can easily lead people astray. They sometimes conjure up images of infinite free energy sources or fantastical engines that run forever without fuel. This is simply not what the Casimir effect is about. It strictly obeys the laws of thermodynamics. To reiterate, the Casimir force causes two plates to move together performing work. To cycle this process, to pull those plates apart again, you must actively put energy into the system. You have to overcome that attractive force. So it's not a way to get something for nothing. It's a manifestation of a fundamental force that is always present. You can use it. But you can't endlessly extract energy from it without an external energy input to reset the system. It's like using a spring. A compressed spring can do work when it expands, but you had to put energy into compressing the spring in the first place. The Casimir effect is similar. It shows us that vacuum energy is real and can exert forces. But harnessing it for continuous work still requires external energy input. The Casimir effect, at its heart, is a rearrangement of the vacuum's inherent energy. It's a pressure difference, a local imbalance, not a creation of new energy. It beautifully illustrates how the rules of quantum mechanics impact the macroscopic world, even if only at very tiny scales. It's also a powerful reminder of how profoundly different the quantum world is from our everyday experiences. We live in a world where objects seem solid, where cause and effect are clear, and where emptiness means, well, emptiness. But at the smallest scales where quantum rules dominate, everything is probabilistic, interconnected, and far from intuitive. Even empty space is a vibrant, energetic domain. The Casimir effect is one of the most direct and startling proofs of this hidden activity. It's a tangible window into the weirdness and wonder of quantum mechanics. This phenomenon truly shows that what we perceive as a void is anything but. It's a dynamic, energetic sea of possibilities, constantly giving rise to subtle yet powerful forces. This force is always there, even if we usually don't notice it in our large-scale world. But at the fundamental level, it's constantly shaping the universe. It's shaping how atoms interact, how materials behave at their surfaces, and how tiny machines will be built in the future. The journey of understanding the Casimir effect, from its theoretical prediction by Casimir and Polder to its painstaking and precise experimental verification, has been a triumph of human curiosity and scientific rigor. It pushed the boundaries of what was technologically possible to measure. It forced physicists to confront the implications of their most abstract theories. It showed us that even the most esoteric concepts of quantum physics can have concrete, observable consequences in the real world. The Casimir effect is a beautiful and elegant example of how the simple act of placing boundaries in space can literally alter the very fabric of reality, at least in terms of the quantum vacuum. It demonstrates how the presence of matter, even just two simple flat metal plates, can change the fundamental rules for the quantum vacuum. It changes what modes of energy, what virtual particles are allowed to exist in a given region. This, in turn, leads to a measurable force, a force that seems to come from nowhere. But we now understand that nowhere is a very busy, very energetic place indeed. And this isn't just a fascinating curiosity for theoretical physicists in their ivory towers. It has very real, very practical implications, especially as we venture further into the realm of nanotechnology. As we continue to shrink our devices, as we build machines and structures at the atomic and molecular scales, these previously unnoticed quantum forces become critically important. Engineers and scientists working on these miniature scales must account for the Casimir effect. He doesn't mitigate its unwanted effects, like scission. And increasingly, they are looking for ways to control and utilize it. So, the next time you look at what appears to be empty space, don't just picture a void. Picture a bustling, energetic environment, an invisible ocean teeming with virtual particles that flicker in and out of existence. A place where forces are born from these fleeting interactions, and picture two metal plates, silently, irresistibly being pushed together. All because of the hidden energy of the quantum vacuum. It's a powerful and humbling reminder that our universe is far stranger, far more complex, and far more interesting than we often imagine. It's also a testament to the sheer power of pure human thought and imagination. Hendrik Casimir didn't have fancy equipment. He didn't have supercomputers. He had a pencil, paper, and a profound intuitive grasp of quantum mechanics. He imagined something no one had ever dared to consider before, and he came up with a prediction that, against all odds, proved to be absolutely true decades later. It speaks to the incredible beauty and predictive power of theoretical physics. The Casimir effect stands as a powerful reminder that there is always more to learn. Even about something as seemingly simple and fundamental as nothing. It's a gateway to understanding the universe at its most foundational level. It's a constant source of wonder and inspiration for physicists and anyone who cares about the deepest truths of reality. And it truly challenges our common sense notions of what space, and indeed, what reality itself truly are. It forces us to rethink everything we thought we knew about emptiness, and that in itself is a truly remarkable thing. It's a force that embodies the quantum world. It is weird, it is counterintuitive. It is a bit mind-bending, but it is real, and it shows us that even in the quietest corners of the universe, there is a constant, energetic dance happening. A dance that can push and pull on the things we build. A dance that shapes the very small. And perhaps even the very large. It's a force born from the deepest mysteries of physics. A testament to a universe that never ceases to surprise us. This force tells us that the universe is not just there. It's an active participant. It's constantly interacting with itself. It's shaping things at every level. From the smallest fluctuations to the grandest cosmic expansions, the Casimir effect is just one tiny, measurable piece of that grand, complex puzzle. And it's a piece that has changed our understanding of reality forever. It turned nothing into something. And that's truly something to think about. The very existence of the Casimir effect highlights a core message of quantum mechanics. Our intuitive understanding of the world, built on what we see and touch, is deeply flawed when we look at the universe's fundamental building blocks. It is a constant battle against our common sense. A vacuum is empty to us, a particle is either here or there. But the quantum world says otherwise. It insists on a more fluid, uncertain, and energetic reality. It's a humble force, really. You don't feel it when you walk around. It doesn't hold planets in orbit. But its significance is immense. It's a bridge. It connects the purely theoretical world of quantum fields and virtual particles to a measurable, tangible effect in the lab. It grounds those abstract ideas in reality. It makes them concrete. This is a very powerful thing for science. It tells us we're on the right track with our quantum theories, even when they sound like wild tales. And this understanding of the Casimir effect, this journey from an obscure theoretical prediction to a well-verified phenomenon, also reflects the very nature of scientific progress. It starts with an idea, sometimes a strange one. Then comes the rigorous math. Then the painstaking work of experimentalists trying to build instruments precise enough to detect something incredibly subtle. There are setbacks, there are frustrations, but eventually, if the theory is robust, the evidence comes through. And then our understanding of the universe takes a leap forward. So, what looked like a simple question, what happens between two plates in empty space? There is motion, there are forces. It's a testament to the endless surprises the universe holds. And it encourages us to keep asking questions, even the ones that seem impossible to answer. Because sometimes those questions lead to the most profound insights. The Casimir effect, a force from nothing, is in fact a force from everything. It's a force born from the fundamental existence of quantum fields, constantly vibrating and fluctuating, filling every corner of space and time. It reminds us that the universe is never truly passive. It is always active, always dynamic, always pushing, always pulling, and always full of wonder. This insight changes how we perceive the universe at its most fundamental level. It tells us that nothing is truly empty. Not really. Every tiny bit of space is alive with potential. It means that the universe is a more intricate, interconnected place than we might have ever imagined. It's a testament to how complex and beautiful the laws of physics truly are, and it leaves us with a sense of awe for the hidden depths of reality. The sheer audacity of Casimir's original thought that empty space could exert a physical force is still inspiring. It shows that sometimes the biggest discoveries come from questioning the most basic assumptions. And because of that initial spark, we now have a much richer, albeit stranger, picture of the cosmos. It's a picture where silence is buzzing and emptiness is full, a truly remarkable shift in understanding. And as technology gets smaller, as we push the boundaries of what's possible with materials and devices at the nanoscale, the Casimir effect will only become more central. It's no longer just a theoretical puzzle, it's a design constraint, it's a potential tool. It is part of our future. Understanding it better means we can build better. We can create things previously thought impossible. Frictionless systems, new forms of propulsion, devices that use the very fabric of space to operate. These are the long-term dreams fueled by this subtle yet powerful force. So the next time you hear about the Casimir effect, remember its story. Remember that nothing is a misnomer. Remember the dancing virtual particles. Remember the constrained wavelengths. Remember the pressure differential, and remember that this tiny, hidden force is a colossal revelation about the universe. It's a force from the quantum vacuum, a force from the very heart of reality itself. And that is far more incredible than any magic trick. It's the real thing.